Yeah, thanks for the kind introduction here. I'm going to present you today joint works with my colleagues from the University of Freiburg, Philipp Scholl and Bernd Becker. We tackle the problem of generating better data sets for non-intrusive load monitoring, especially for high-frequency non-intrusive load monitoring on residential buildings. Therefore, why do we need good data sets at all? So if you want to deploy a NILM system, the first thing you do is you use a set of NILM algorithms, you use a set of evaluation metric, or just one evaluation metric, and you use a set of data sets, and then you evaluate the NILM algorithm and choose ultimately the one that fits your needs. Then you deploy this NILM algorithm in the NILM system and apply it to live data, right? And at the end of the day, you get device profiles, we have talked about it, and also device state information if the algorithm supports this. On top of this, you can also integrate other feedback systems, for example, electricity feedback systems, or something like a human activity recognition system. But the quality of these systems highly depend on the quality, of course, on these profiles and on these state estimates, and therefore on the quality of your NIM system, and ultimately also on the quality of the data sets. Therefore, we summarize some challenging for generating better electricity data sets. So the first challenging is that as a residential building, so a home is basically a distributed setup. So you have devices in your basement, for example, you have on your rooftop, and you want to send the data from these devices to a particular data sink in the house. Therefore, you require wireless transmission, obviously, and therefore also something like time synchronization. We've talked about before, let's call it high sampling rates, even if you don't know what high means. We want high sampling rates because so that we cover the largest set of algorithms we can apply to the data set. But this, of course, leads you to have to use expensive hardware, and at the end of the day, you have lots and lots of data, right? Furthermore, we want precise ground truth. We have it for labeling is a tedious process if you do it manually. So we thought, why not do it a little bit more in a semi-automatic fashion? And last but not least, it should be easy to use the data set, so it should be easy to generate it at all, to load it into RAM, of course, and to provide it in other sampling rates as well. For example, if your algorithm only requires 1 Hz of data, you don't want to load in, 32 kilohertz data. But due to time constraints, I will today focus on these two, so on the hardware and on the labeling process. Let's dive into the hardware. To get like smart meter data, so aggregated data of the complete home, we have developed our own measurement system here, which can measure 3 times current and 3 times voltage at up to 32 kilohertz. As you can see here, it can be installed in the fuse box pretty easily, and you can, for example, attach a PC next to it and get the sample data out of over a wired interface, over USB, but you can also get the data out over a wireless interface, so we have Wi-Fi on board. And as you can also see, we have a USB connection here, and we also have a direct connection to 230 volts, so we have to make sure that interfacing with the system over the USB connection is safe. And therefore, we talk IEC, so we are compiling to a lot of IEC norms here. To get circuit level data, so device level data, we also developed our own measurement system here, which I also have with me, this ugly little gray box here. Which can sample voltage and current at up to 8 kilohertz. There's also a relay inside it, so you can switch 16 amp devices on and off. And there's also a real-time clock inside. So this is for clock synchronization and also to get precise timestamping. Again, the data can be either sent wirelessly to a data sink, Wi-Fi or Bluetooth, or over a USB wire connection. Again, here we're dealing with USB and 230 volts, so we have to make sure that everything is protected. So how do we get now data out of these measurement systems? Therefore, you require a recording PC and a recording framework, and this recording framework then sends a request to all the devices which are either in the network or connected over USB to stream data at a specific time of day. And then these devices sync time using the network time protocol and start streaming the data to this data sink. The PC then has an accurate wall clock to timestamp this data. And as we use multimedia streaming solution here, in particular we use FFmpeg here, we store the data from all of these devices in a single file. Since we use this multimedia streaming solution, we can apply nearly any audio compression to the data and also nearly any file format to the data. We ultimately choose to use the WAV-pack encoding and the Matroshka multimedia container because it also allows us to store like ground truth inside the data as subtitles. But so far, we don't have these ground truth information yet. So far, we basically have the same as all the other data sets out there. So we have like device level information like here, desktop fan, where you can see the state changes, but they're not annotated. But what we want is basically exactly this. So we want the exact time time when a state change occurs and when the power increase occurs, for example. And we also want the information which state the device is in. For example, for this desktop fan, that would be speed settings of the desktop fan. It has just 3 speed settings, which one button you can traverse it through all these settings. Of course, you can do this manually after the recording. So you can use, for example, subtitle editor software, load the Matroshka file and edit it there, export it as another Matroshka file. But that's a tedious process, as I mentioned. And therefore, we assist this process by using a post-processing step so that you only have a human refinement step at the end where you have to like delete false positives or add false negatives. This post-processing step is basically doing 2 things. First, it tries to classify the connected device into one of the 4 categories introduced by Hart. I think you all know them. And secondly, it tries to reveal internal device states. So therefore, we utilize state change detector to get the time in the signal when the state change occurred. And we also try to get all the unique states. So we make something like a clustering analysis of all the seen steady states. And to also recognize these category 4 devices, we use a high variance detector. And at the end, we can also then generate out of the data such an appliance model as you can see here for a simple on-off device. So let's dive into the state change detector here. It is based on the log likelihood ratio by Pereira et al. And basically using 3 windows here. So the pre-event window, the post-event window, and the voting window. As you can see here, this pre-event and post-event window, they share the same J. So it can be put together like to the event window, which you can then slide over the data. So you increment J here. And then you calculate for each J the following formula. So you basically calculate the mean value in the pre-event and the post-event and also the variance, put it into the formula and get something out like this signal as shown here, which is kind of noisy, but it shows some peaks where the state change occurs. And we thought, why not denoising the signal a little bit? So we force it to 0 if the state change from the pre-event to the post-event is below a certain threshold. And the threshold is not fixed, no, it's linearly increasing with the mean value of the pre-event window here. Then we get this clean signal here. To ultimately get the time when a state change occurred, we use this 3rd window, the voting window, to find the maximum of the absolute value inside this window, which corresponds to the state changes as shown here. And using the result of the state change detector and the clustering analysis, I could not talk because due to timing, we can then annotate this data so that we get what we want actually. And we also can generate such a finite state machine, which is shown here at the bottom, which we can, for example, use to train algorithms. We also evaluated this post-processing step by recording a data set and comparing a manually labeling of this data set with automatically labeling. And therefore, we recorded 42 devices with our socket meters here. These are of category 2, 3, and 4. And we labeled all state changes there internally manually. We applied the parameters, which are shown here. And let's come to the results. So I split the results in terms of category according to Hart. So you can see here that category 2 devices perform pretty well. So we get an F1 score of 97% here. And if we add category 3 devices also to the set, then we get basically the same 97% as before, but only if we add category 4 devices, which is the first row here, then we see a huge drop. So we can say that basically it does not work well for category 4 devices because there you have like variance in the signal, and it will trigger, as you can also see here, a lot of false positives and false negatives. if you now have the recording hardware, the recording interface, and the post-processing step, you can build this together into a framework to record data sets of high entropy. For example, as you can see on the right side, where you have your aggregated signal on top with all the state changes marked, and also the individual device streams at the bottom with precise and high entropy labels there. You can use this dataset then to apply to event-less NILM approaches, to event-based NILM approaches, and also to like human activity recognition approaches where you want to precisely know what the device is currently doing at the moment. And of course, it's easy to generate it, as I've shown you, and to regenerate. Let's conclude this. What I've shown you is a hardware and software framework to record advanced data sets. It can sample at aggregated level up to 32 kilohertz, at socket level at up to 8 kilohertz, and all the data is stored together in a single multimedia file, together with its ground truth, which can be generated in a semi-automatic fashion with at least good results for category 2 and 3 devices. Therewith, the labeling effort for generating such a dataset is significantly removed, and at the end of the day, you also get these finite state machines of the appliance model. For future work, what's currently in progress, I told you we can generate good datasets, so we're actually generating one currently. Therefore, we have built like 50 of these ugly boxes, and are deploying it currently in 2 homes to record a large dataset. That's it for me. Thanks.